Today we're going to talk about stretch directions and stretch factors, which are also called eigenvectors and eigenvalues. So a non-zero vector v is called an eigenvector of the matrix A if the effect of multiplying by A is to multiply the vector v by some number. What's important here is that the vector v and AV live on the same line. So in other words, our matrix A is going to stretch v by a factor lambda. This direction in which our matrix is just stretching is called a stretch direction, or an eigenvector. And the amount that it stretches by, this factor lambda, is called a stretch factor, or an eigenvalue. So let's take a look at a picture to see what we're talking about. So I'm going to suppose that the vector v is an eigenvector. When I apply the matrix A, the result is going to lie on this same line that contains the vector v. Okay, so for instance here we have compressed our vector a little bit, but it lies on the same line. This is in contrast to, say, this vector w, where we expect that after multiplying by the matrix A, we get some other vector, but there's no reason that it should lie on the same line as the vector w. And we can see here it definitely does not lie on the same line as w. Okay, so v is an eigenvector for this matrix A, and w is not. Next, we're going to look at how to decide whether or not a vector is an eigenvector, and then what its stretch factor is, what its eigenvalue is. If we have a vector and a matrix in hand, it's really easy to check whether or not we have an eigenvector. And if we do have an eigenvector, we'll be able to find its eigenvalue very easily. All we're going to do is we're going to calculate AV and compare it with V. Okay, so we want to know whether AV equals lambda V for some lambda in R. So here we have our matrix A, and we have two different vectors to consider. Let's calculate. So if I multiply A times V, I get 15 plus 6 plus 4 as my first coordinate. And let's see, 18 plus 12 as my second, and 6 plus 4 as my third. So A times V is equal to 25, 30, 10. This vector, 25, 30, 10. And now I'm going to compare my vector AV with the vector V. V is 5, 6, 2. And now we can see, well, the vector AV is exactly 5 times the vector V. This implies that V is an eigenvector, and its eigenvalue is 5. It's stretched out by a factor of 5. Now we can do the same check with the vector W, if we want to know whether or not W is an eigenvector of the matrix A. So I'm going to calculate A times W, and I get 6 minus 1 plus 2 as my first coordinate, negative 3 plus 6 as my second, negative 1 plus 2 as my third coordinate. And we can simplify this as 7, 3, 1. Okay. Again, I'm going to compare with the vector w. And it's easy for us to see that this is that AW is not equal to lambda times W for any lambda in R. For instance, if these were going to be equal, our last coordinates would tell us that lambda would need to be equal to 1. But if we compare the middle coordinates, this says that lambda should be equal to -3. Since we can't have both true, we see that AW is not equal to lambda W. And so the vector W is not an eigenvector of A. Next up, we are going to look at how we find these eigenvectors.